Okay. Are we good on that one? Do you want any more? Do you have any other questions?
Yeah, that was really helpful. I think I just got like stuck right off the bat, just trying to understand like
Okay. So this lab is due when?
Monday.
Monday. Okay. So you got time to throw some more questions at me if you run into some more roadblocks, because I'm going to be honest with you. This whole lab is our questions kind of like that.
Yeah. Yeah, actually it was pretty helpful because I actually did most of the beginning correctly. I
Good.
think it's just where I got stuck was just basically trying to pick that whole resonance structure concept and trying to figure out which one is better. And I think that's where I got stuck.
So here, I've got a question for you as long as we're looking at this. Do you see the nitrogen-nitrogen single bond length,
Yeah.
the nitrogen-nitrogen double bond length,
Yeah.
and the nitrogen-nitrogen triple bond length?
Hmm.
What's the pattern for those links?
Well, the more bonds you have, the shorter the bond length. I
Now,
mean, the
doesn't that
more you have, the shorter the bond length gets.
doesn't that seem odd? Because more bonds means more electrons, right?
No, it's not odd because you have more electron force. What is it more like?
Well, here's the way to explain it. Those
Yeah,
electrons are pulling the nuclei together.
right, exactly. Electrons
The
are.
nuclei don't want to get together because they're positively charged, right?
Mm-hmm.
But the electrons apply that force to bring them together because opposites attract. So putting all that opposite in the middle helps actually bring the protons together.
Okay.
And that's essentially what's going on there. So I think the way you describe that is electron force, but it's the attraction of the electrons for each nucleus that brings them together.
Okay.
And so here you could use the family analogy. The tighter family is the one that has more people bringing everyone together,
Mm-hmm.
right?
Mm-hmm. Okay.
Okay, so do you see how the next one is nitrogen dioxide? How is this one going to be weird?
Hmm.
Let's start off. How many electrons does it have?
So we have nitrogen with 5 and then plus 12, 17.
So what makes that weird?
I feel like that means that the structure is going to be, let me see,
Well, let me ask you this. How do you place electrons
by
on
8.
atoms after, yeah, you put them on eights, right?
Right.
Okay, so you've got an odd number. How are you going to get 8 on each?
Aren't you just gonna have like an extra one that you put on the nitrogen?
Okay, but then if that nitrogen has a single, it's got to have another single to have 8, or it's not going to have 8.
That's true. It's odd.
And can you just magically invent another electron and say, oh, here's one, I found it?
Nope, you can't do that.
You can't do that. So
Hmm.
none of these atoms can have more than 8.
Hmm.
So guess what? One of them has to have less than 8. So that's what
The
makes this.
nitrogen?
What's that?
The nitrogen can have less than 8.
Well, I think that's what we have to go for, right? Because oxygen is more electronegative. It wants electrons more. So if there's going to be an atom that's not going to have enough electrons, I'd say it'd be nitrogen because it doesn't want electrons as much as oxygen,
Right. Hmm.
right?
Yeah, that's what I
So
was thinking.
that's what makes this one interesting is you have an odd number of electrons.
So we can just leave the nitrogen with like a missing electron.
It's not like you can, it's like you have to.
Hmm.
It's not a choice. It's a must.
Yeah, this is what's tricky about these. Because I
Yeah.
think like, oh, they're easy. And then I start doing them. I'm like, wait, I'm super like, why is this like that? It's not
Now,
easy.
NO2 -1, number 3. How many electrons does that have?
So it's going to have an extra electron. So it's going to be 18. So it should be better.
That should be better because it's at least even. How about the NO2 +1?
That's going to have a missing electron. So it's going to be 16, right? So it should be better too.
Right. Instead of 17, it'll be 16.
Mm-hmm.
So we do that one. So these are supposed to give you practice drawing resonance structures, looking at them, looking at formal charges, and seeing what's going on.
Okay.
Okay.
Yeah, they just get tricky. I feel like it's just about practicing. But I feel like the ones we did yesterday were not as hard. And then I was like, what? I feel like
Yeah.
when I did the first one, I was like, what? This is not as easy as the ones that we did.
The homework is always harder and the labs are harder because I'm trying to make you dig into the detail and think about them.
Yeah. Okay. So yeah, I think I feel a lot better about the lab now after going through
Excellent.
one.
Okay, well then I'm going to let you go. I'm sure you want to get to it.
Yeah. Yeah, I don't have any other questions right now, but if you wanted to like do something else, you can.
Well,
Or
it's up to you. What is going to help you the most? Me going through some problems with you, or you working on these on your own?
yeah, I think I just need to work through the lab. I just want to make sure I understand the structures because I thought I did, and then I started working on the lab, and I was like, I guess I haven't fully grasped it yet.
Okay. So you want to work on these on your own then?
Yeah, I guess I'll work on them on my own.
You sound like you're hesitant. Do you want me?
No, I mean, if you want to, you can. I don't want to take up your time.
Okay, look, Issa. I've got another 15, 20, 30 minutes that I can help you. All I
Okay.
need to know is that you want the help or you don't
Yes.
want the help.
Yes, I can go through it with you because that way I know I'm doing it correctly.
Okay, so I'll tell you what. So to really help you out, we'll look at number 2 next. And you go ahead and get the Lewis structure, and I'll get the Lewis structure, and we'll compare the two, okay?
Okay.
All right. So let me make sure my share is here so you can't see what I'm doing.
So
Okay,
the nitrogen can have less than 8 or more than 8.
anything in period 2, everything in period 2 can have 8 maximum.
Okay.
You cannot go above 8.
Okay. Well,
Which
I
means you can
think,
go less than 8 if you have to.
yeah, that's what I was thinking.
Okay, so you should have 2 resonance structures.
Well, I've only done one so far. Well, I guess, oh yeah, because then the other one is just the other side. So it's like the same but reversed.
Okay, so now let me share with you what I got. And what I did here is I kind of went through it step by step. First, 17 electrons. Next, nitrogen in the middle with oxygens on the wings. Next, octets on oxygens, I'm sorry. And that's only 16 electrons, so I had to put the last electron on nitrogen.
Yeah.
And then I'm trying to get an octet on nitrogen. And so I borrowed a lone pair from this oxygen and made a double bond. And now I have 7. And here I borrowed a lone pair from this oxygen and made 7. And we're not going to do this. So this means no. Okay. And here's my explanation for why no. Nitrogen cannot have more than 8 electrons, period.
Right. So that's what I started off with, but then I was like, that's why I asked you, like, okay, can it be more? And I'm like, oh wait, I think you said it had to be less. So then I came up with the same thing.
And even in the problem, it says you can't have more than 8. So do you see
Oh,
this?
yeah.
Where is it? Period 2 elements cannot be hypervalent. They can only have an octet at a maximum. So hypervalent means more than 8. Okay, let's evaluate each using formal charges. So you assign formal charges and I'll assign formal charges, and then we'll see what's going on, okay?
Okay.
Okay. All right, how are you doing?
Yeah, I think I'm done.
Okay, so here,
It's basically the same for both, right?
well, except for on one,
Mm,
on the oxygen that has a double bond, it's a 0.
right.
The nitrogen is a +1, and the oxygen with the single bond is a -1.
Mm-hmm.
So if that's what you mean by the same, then yes.
Yeah, I mean, like both structures have the same. It's just,
The same set, but the oxygen
yeah.
is reversed.
Mm-hmm.
Okay, so which one's better?
Yeah, I think that's what I meant. They're the same.
So they're equal.
Yeah, okay.
So if we take a look here, if they're equal, what is this nitrogen oxygen bond order? What do we think it's going to be?
Mm,
Because you see this, the deal is neither of these is correct by itself. They're correct
right.
together. So
Mm-hmm.
this oxygen is this oxygen. This nitrogen is this nitrogen. So what's the bond order in this one to the right?
2, 1,
And this one on the left is a 1. So what's the average?
1.5.
Good. And how about here and here? What's the bond order equal to?
It's also equal to 3 and then divided by 2,
So 1.5.
1.5.
So hopefully what we'll find out is that both bonds are equal in length because number one, they're both a nitrogen oxygen bond. And number two, they're both 1.5.
Okay.
Now, do you remember those numbers we had from before? Those numbers we had from before were that a nitrogen, nitrogen single bond, and a nitrogen, nitrogen double. Oh, actually, we don't want nitrogen, nitrogen. We want nitrogen, oxygen. If we look at the lab, so I'm going to do a new share. Can you see that we can actually use numbers from the previous problem that says a nitrogen oxygen single bond is 147?
Oh, okay, yeah.
And what is a double bond?
A nitrogen oxygen double bond is 115.
Okay, so if this is a bond and a half, we would expect it to be somewhere in the middle of those two, right?
Mm-hmm.
And let's see what this actually says. Oh, it's actually 124.
Yeah. Okay.
And that is not directly in the middle, but it's not really close to 115 and it's not really far from 147.
Mm-hmm.
So it kind of makes sense.
Right.
Okay, so that's how, does this make sense? You could say, here's what I would write. I'd say, yeah, it does make sense, but I'd expect it to be closer to, you see that 147 and 115, that the difference is what, 32?
Yeah, so
Half of,
147
yeah,
plus
half of 32 is
115,
16. So I'm thinking, I would expect,
131.
what's that?
131.
Yeah, I'd expect it to be closer to 130 than it is to 124. That's the only comment I would write is it does make sense. It's because it's in between those two values. However, because 1.5 is halfway between 1 and 2, a single bond and a double, I'd expect the bond length to also be about halfway, which is 130, about 130. But it's not so far off, right?
Mm-hmm. Okay.
So number 3, do you see the same question, basically?
Yep. Mm-hmm.
Now here it says, what is the expected bond length? And I don't give you the real one, do I?
Okay, so we're just supposed to estimate based on the
Yeah,
numbers that were given before. Okay.
you can give a range, or you can give, I think it's going to be this number, something like that. Now, do you know why I did not give you a number to compare that to?
So we could use the approximate bond. What is it? The bond order to come up with an estimate?
Nah, I couldn't find it online.
Oh.
See, you think I'm always being sneaky, but nah, I couldn't find it. How about number
You
4? Do you know why I
you
didn't
just accidentally made it harder for us.
number 4? Do you know why I didn't give you the bond length?
Could not find it.
I couldn't find it.
Is there ions? Maybe it's harder.
Yeah, and there may be resonance structures for these.
Okay.
So meaning that you might have a double bond and a single bond, that kind of stuff.
Okay.
Okay. So I think doing number 2 is helpful. Did you want to look at number 3?
Yeah, if you have time, I would
Sure.
like to go through it just to.
So number 3 is NO2 minus. So I want you to go through all of these.
Yeah. Mm-hmm.
And then let's compare. While you're doing that, I'm going to do the same. Okay, so NO2 negative 1. And before we get too far ahead of ourselves, how many electrons do you have?
18.
Okay, that's what I have too. Now this time you should be able to get octets on everything.
Yeah.
How many structures did you get?
I think it should just be 2.
That's what I got. Now assign formal charges.
So it's very similar to the previous one.
Yes. Now, there is one more thing with the 2 structures you get. You need to put brackets around it plus a -1 on the outside because that's what you do with ions. So once you get your formal charges, let me know.
Oh, okay, I was like, I don't know why at first I was thinking like it's not neutral, and I'm like, oh wait, it's supposed to be, they're supposed to be a negatively charged.
So all of your formal charges added up to -1, didn't they?
Yeah,
And they're supposed to. So did you get like a 0, 0, -1 where the single bonded oxygen is -1?
correct.
Okay, now I want you to give me the bond order based on both of these being correct because there's no real difference between them, right?
Yeah.
So
So,
the bond order,
do you mean like the average, like 1.5 or?
yeah, the average.
Okay, that's that's what bond order is, or what's bond order? Is it just like, I thought bond order was like 1 bond, 2 bonds, or like,
It is normally. If there's only one structure, then bond order is the number of bonds. But when you have resonance structures, bond order is the average.
okay. So it's just 1.5.
For both of them, right?
Okay.
And for both of them, I mean the one to the left and the one to the right.
Mm-hmm.
Because the way these atoms are, so I'm going to do a new share. What we need to understand here is that these 2 resonance structures, neither is correct. Neither is correct by itself. So we draw both of them to say it's an average of the 2. We can't really draw the average. It doesn't work that way. But if we take a look here, if this is oxygen number 1 and this is oxygen number 2, it's the same here. This is 1, this is 2, this is 1, this is 2. So you see these 2 oxygens?
Mm-hmm.
They're not 2 oxygens. They are the same oxygen.
Mm-hmm.
We're just looking at the molecule from a different arrangement of electrons. That's all.
Yeah.
And these are the exact same oxygens also. So what is the bond between this nitrogen and this oxygen if it's a 2 here and a 1 here, and both of these are equal? Well, it's an average of the 2, 1.5.
Okay.
So this is just like our previous problem. It's a 1.5, and we
Mm-hmm.
expect the bond length to be shorter than 147 picometers because that's a nitrogen oxygen single bond, and longer than a or 115 picometers because that's a nitrogen oxygen double bond. So the best we can do here is it's going to be between 147 and 115.
Right. So around 131.
Right. So here we say maybe around 131. Now, the cool thing would be is if we could actually find out the bond length, and compare it to the previous one, which happened to be a little shorter than we thought it would be, that might tell us something about this being a 2 electrons or 1 electron, right?
Mhm.
But I don't know what the length is. So the next one is NO2 plus 1. Try and go all the way through that, and we'll compare our two, okay?
Yeah.
Let's see, the question is, so now before you get too far ahead, how many electrons did you get?
16.
That's what I got.
So I think this is just one structure.
Absolutely. Because if you do anything else, you won't get an octet on nitrogen, or if you do get an octet on nitrogen and you do a triple bond and a single bond, the formal charges are +1, -1, and +1. So here, I'm going to show that to you.
Yeah, I'm done with mine.
Okay. So do you see these two here?
Mhm.
There's a clear winner. 2 zeros and one that's not a zero is the clear winner. Winner, winner, chicken dinner. That one doesn't count.
If we just drew the first one, is that okay?
Well, that's the one we want.
Oh, okay.
Okay, so what do we expect the bond length to be?
And then we have to put this in a bracket as well with the
That's right.
plus at the
So,
top.
positive. That's right. And here, what is the bond order for this oxygen-nitrogen bond?
That's just 2, right?
Okay, how about this one?
It's just 2.
Yeah.
So we have to
We
put
don't
2 comma 2.
yeah, we don't have to average it with anything, right?
Oh, so you write them separately
Yeah.
with an arrow pointing to each of them. Okay.
Or you could say all bond orders are 2.
Okay.
Okay, so what do we expect the length to be?
Which I think it's 115.
115 picometers. That's it. So once you get rolling on this, it's not so bad, is it?
No, I think I was just really stuck in the first one. Like I feel like that first one really threw me off.
Okay, and guess what? The last one I'm going to just have you do on your own.
Yeah, I think I'm good.
I am going to warn you. For this one, there's like, let me think. There are 4 resonance structures.
Wow.
4 of them.
But the what is it? Let me see. So the phosphorus will be in the center. And then there's
Absolutely.
like four oxygens.
So if you draw 4 oxygens around it, each with an octet, that's 8 electrons for each oxygen times 4 is 32 electrons, right?
Yeah.
Now we kind of did that before counting electrons, which is not good.
29 electrons.
Okay, but it's got a -3 charge.
And then plus 3. Yeah. So it is 32.
So it works out. Great. What's the formal charge on oxygen?
Um, the formal charge on oxygens. I haven't placed the electrons yet. Does it have to look a particular way? So you're gonna have like an oxygen on the right, on the left, on the top, on the bottom,
You can do it that way, or you can
like
put
a
it,
cross.
or you can make it look like an X if you want. It's your choice. It doesn't really matter.
I think it just gets more confusing if you don't draw it exactly parallel.
Well, here's what I'm going to show you. Okay, do you see the way I've drawn it?
Yeah, that's what I got.
But I could have drawn it that way, like an X.
Right.
It doesn't
Mhm.
matter.
So all of the oxygens are gonna have a charge of 1, 2, 3, 4, 5, 6, 7. So negative, they're
That's
all
right.
gonna have a negative charge.
And what's the phosphorus going to be?
And well, actually, I'm a little bit confused now because the phosphorus, um, wait, 1, 2, oh yeah, it is an octet. I remember in my head I was thinking something else had to be done. Okay, yeah, so the phosphorus, 1, 2, 3, 4, it's going to be it's, it has an extra, no. Yeah, it has an extra electron.
Extra? How many is it supposed to have?
3.
No.
No, wait.
A, phosphorus.
Oh, wait, 5. It's supposed to have 5, so it's missing one. Yeah, so it's positive. Yeah, that makes more sense because it's a
Okay.
-3 charge.
Now let's check it another way. What should all the formal charges add up to?
-3.
Do they?
Yep.
Okay, so we double checked it. Now, I got to tell you, whenever you see a resonance structure where all the charges are not zero, you get worried.
Hmm.
So how can we make this better? How can we make this formal charge on phosphorus become a 0?
Um,
Put an
so you would
electron.
have to take a pair from one of the oxygens.
So are you suggesting something like that?
Yeah, on one of the oxygens.
And the rest stay the same?
Um,
Let's
let's
give it a shot and
see.
see what happens.
So we can't have phosphorus with 10. It's not an octet anymore.
We can.
We can?
Anything in period 3 or above, 4, 5, 6, can be hyper.
I need to memorize that. Where is it? Did you give us a chart in that in our lectures? You probably did.
Somewhere.
Yeah.
But anything in period 3 and above can be hypervalent.
Oh, okay. So that's it. That's just 2 things you have to know.
Yeah. Period 2, you need 8. Period 1, you need 2.
Right,
Period
but that's
2,
just
period
2.
2, 8 is
Yeah.
the maximum. Period 1, 2 is the maximum. Period 8, 8 is the max. Whoops. Period 1, 2 is the max. Period 2, 8 is the max. And then period 3 on up, 14 is the max.
Oh, wow.
So this fits well within 14, right?
Yeah.
Okay, so what are the formal charges here?
8 max. Okay. So looking at this other structure. Sorry, I just drew everything really large and now I'm like, I don't know why I'm drawing everything so big on my paper. Okay. So let's see, you got 2 here. On the phosphorus, 1, 2, 3, 4, 5 is 0.
Okay, we like that. How about that oxygen with the double bond?
The oxygen with the double bond, 1, 2, 3, 4, 5, 6. Yeah, that's also 0.
Okay, how about an oxygen with a single bond?
Yeah, so all the oxygens with the single bond are actually negative. 1,
Okay,
2, 3, 4,
so
negative 1.
oxygen is the most electronegative atom there because here's oxygen, here's nitrogen, here's carbon, and here's phosphorus. Oxygen is greater than nitrogen. Nitrogen is greater than phosphorus. So if nitrogen is bigger than phosphorus and oxygen is bigger than nitrogen, oxygen has to be bigger than phosphorus, right?
Hmm.
Like, let's just give them numbers. If phosphorus is a 2 and nitrogen is I don't know, a 3, and oxygen's a 3, 5, is phosphorus smaller than nitrogen? The way I've drawn it?
Yeah.
And is nitrogen smaller than oxygen?
Hmm.
And that's the way we want it, right? The one to the right is bigger, so 3, 5 is bigger than 3, 0. And the one above is bigger, so 3, 0 is bigger than 2. So is oxygen bigger than phosphorus?
Yeah.
And that's the way it should be. So here, our more electronegative atom has the negative charge, which is what we like. Now, we had great luck with putting a double bond to one of these oxygens. Let's try putting a double bond to another one. Because I said you could have as many as 14 here, right? Because it's in the third period. I'm talking about phosphorus, of course.
Hmm.
So here I put a double bond on 2 oxygens. Let's assign formal charges.
Okay, so 1, 2, 3, 4, 5, 6. The phosphorus has an extra electron, so it would be a negative 1.
Okay.
And the double bonded oxygens, 1, 2, 3, 4, 5, 6, are both 0.
Right. And how about the single bonded ones?
Let's see. The single 1, 2, 3, 4, 5, 6, 7. So they have an extra electron. So you got negative and a negative.
Okay, so take a look at this. We still have 2 zeros and 3 ones, like this second one here that I'm pointing at.
Hmm.
Is one of these better than the other? And the answer is yes.
Right.
This one's better because we don't have a negative on phosphorus, and here we do.
Right.
We do not want a negative on phosphorus because it's not very electronegative. We want our negatives on oxygen, the more electronegative atoms. You with me?
Yeah.
And if we try to do this further, like a third triple bond, like this, we would find out that we're getting way too far down the rabbit hole. Because here, in this case, you would have a 0, 0, 0, -1, and a -2. What do we think about 2s?
We don't like them.
No, we don't not like them. We will not put up with them. They've
Hmm.
crossed the line. 2s, no, absolutely not. This is like the parents who decide, we're only going to have one kid. No. Okay. So that's it. Just like, one dog families, one dog, that's it. We're not going
Yeah.
to,
Yeah.
and certainly not 3, and certainly not 4.
Right.
Okay.
Okay.
So do you see that considering these two, it's got to be this one and not that?
Yeah. Hmm.
So how many ways can we draw this with a double bond between oxygen, but only one double bond?
Like 4, no, wait, 3, 4 different ways.
3 additional ones.
Three additional ones. Yeah.
Double bond up, double bond right, double bond down.
Yeah.
So do you remember when I told you before there are 4 of them?
Hmm.
This plus 3 more.
Okay, that's what I was thinking. Okay.
And to just kind of give you the short of it without writing it all out, here they are. Double bond up, double bond right, double bond down, double bond left.
Okay.
And I'm not putting all the oxygens in because
Hmm.
you know what? That's your job, not mine.
Yeah. Okay. So basically, we have to understand how to like try to get the structure to be more correct. So like it may not be initially what we thought. Like we might have to create more zeros or make sure that the zeros are or the negatives are the on the most electronegative.
Yeah. And what this is called it's called the electroneutrality principle.
Hmm.
And the idea here is that you want the more stable resonance structure is the one where there isn't a lot of charge buildup all over the place. So how do you know there's not a lot of charge buildup? Well, because you have 0 formal charges. That's how you do it.
Okay.
So if you are going to have charges in there, where do you want them? Well, you want them on the atoms that can sustain the charge, the more electronegative atoms.
Okay. Okay.
So that's why they call it electroneutrality, is because it's based on electrons, but it's also, you're looking for neutral formal charges, essentially.
Yeah. Okay. Yeah, this was really helpful.
All right, so I think you got this lab.
Yeah.
You
Pretty much did it all right now.
do it. Once you start doing it again, you're going to find out it just gets easier as you go along.
Yeah. You just saved me looking through my textbook aimlessly.
Okay, good.
I would have probably spent all this time like trying to see if I could find something in the textbook to help me.
And
Because
that's
yesterday I was looking through the textbook to find some more information on the bond lengths,
uh-huh.
and there wasn't that much information on the textbook on bond lengths, and I was like, what?
Well, it's more towards the end of the chapter, I believe.
Oh, okay,
We talk
okay.
about
Maybe I
bond
wasn't.
length, bond order, and bond strength.
Oh, okay. Maybe I wasn't looking at on the right place. At the
Honestly,
right place.
it may not be in this chapter. It may be the next chapter. Let me see. Polarity. Yeah, it's in here. So do you see here bond properties, order length, and dissociation enthalpy?
Oh, I was looking for it at the wrong spot.
So it's at the
Okay.
end. So order means how many bonds, length means how long is it, and dissociation enthalpy simply means how easy is it to break. So what do you think is going to be easier to break? Carbon-carbon single, carbon-carbon double, or carbon-carbon triple?
The single bond.
Right. Which one's the shortest? Carbon-carbon single, carbon-carbon double, or carbon-carbon triple?
The triple bond.
The triple. And which one has the largest bond order? Carbon-carbon single, carbon-carbon double, or carbon-carbon triple?
The largest bond order, the
Yeah,
triple.
triple, because it's a bond order of 3, right?
Yeah.
So large order, high order, means short length, but also means high enthalpy, dissociation enthalpy.
Right. High enthalpy.
So it's kind of like high, low, high.
Yeah, that makes sense. It's kind of like if you had like bands or something, like rubber bands.
Yep.
And you
Or
think like
think of it
more.
as like dots of glue between two things.
Hmm.
3 dots of glue might hold things together better than 1 dot of glue,
Yeah.
and harder to
Yeah.
break.
Yeah. True. Okay. Yeah. Thank you so much.
You bet.
I'm like basically done with my lab. I just have to
What?
go through it and make it nicer.
Okay, and here's, I think, didn't I say about this one that you don't have to write it up in your lab notebook?
No, yeah, you said you don't have to write, we don't have to write it. Do I have to write it in pen or pencil?
Well, no. You only have to write things in pen in your lab notebook.
Okay.
So if this is something you just need to turn in, I don't care if it's in pencil or pen, it's your
Okay.
choice.
All right. No
Fair enough?
problem. Got it. Thank you so much, Tony.
You're welcome.
All
Have a
right.
good
Have,
day, Lisa.
all right. Have a good one. Take care.
Bye.
Bye.